I should mention, as some of you would know, that after every class, these videos are posted in Microsoft SharePoint thing, and are also posted on YouTube. So I've been recording all of my classes for several years now, like dating back to like 2016 or 2015. So if you're taking more math classes, there'd be a playlist for each one. So think of it as another resource. So for instance, you can find all the videos I have like in Cal 4 or differential equations or something like that.
What's your YouTube channel?
Oh, my YouTube username is JV Lambers.
JV Land.
Yeah,
Maybe Lambert's gaming channel.
yeah, because I totally have time for that.
He's streaming the Fortnite wins.
I'm more of a Wolfenstein guy.
Hey,
Culture.
So, I've actually last week for some while I was playing the original Wolfenstein.
yeah, I've been playing the original. I've been playing the original.
My God,
1982.
mercy in your soul.
Did you ever play the original Fallout game?
No,
Those are actually fun.
I've got both lately.
yeah, because I played it in 1982 on my Apple II Plus. Long before any of you were born, I guess. Right. But yeah, but certainly if you follow any of the links to the YouTube video from the Canvas discussion, then you can get to my channel from there. Okay, I've been looking at like a playlist and see what's there. Okay, now, so over the weekend I put together the next homework 3. That'll be on the material that I'm covering today. The Wednesday's class, that'll be homework 4, and I've prepared it. It's not posted yet, but it will be. So that's a bit basically the usual policy of once I cover a section, you have a week to do it. So the due dates might bunch up a little bit. If there's any wiggle room, I'll spread them out. So I have to look at the calendar to see what's coming, because around the time of the midterm, there's going to be a gap where there aren't any new homeworks, because you'll be stressing out over midterm. Okay. So
And when is homework 3 due?
homework 3 will be due a week from today.
How much?
And homework 2 is due
Wednesday, yes. And I try not to put too many problems on them. Okay. Yeah, so these next 2 sections in my notes are all about, given a series, how can you determine whether it converges or not? And for what I show you this week, we're not going to be able to figure out what the sum is if it converges. We're not trying to answer that. We're only asking, does it converge or diverge? So I'll be covering some tests that you can use today, some more on Wednesday. So I literally called the sections some conversions tests and then other conversions tests, because I couldn't decide what else to call them. Okay, I mean, you'll have a homework assignment on each one. So in my notes, I spent a fair amount of ink like deriving the tests involved. I'm not going to get into that here, just because it's not necessary for the homework and it would take way too much time. So what I'm going to do here is I'm going to describe, okay, here are the tests, here's how you perform them. Here are several examples on how you do that. That'll put you in good shape for the homework. And then if you want to know more about the justification for these tests, why they work, then you can find that in the notes. Okay. So given a series, some n going to infinity of some expression a sub n that describes the terms of your series. converges or diverges. Okay. Now, the very first test I'll tell you actually is not a test for convergence. It can only tell you about divergence. It's called the nth term test or divergence. So this is a relatively simple way to rule out a series converging. So all it says is, if you look at the individual terms of a series, AN, and you go, and now, so now you're thinking not about a series, but rather a sequence. The sequence, AN, is not zero, then the corresponding series diverges. Example. Okay, so this is our series. The terms are n squared over n squared plus 3. You go ahead and take the limit as n goes to infinity of the expression that you're summing up. What is the limit of that sequence? There's various ways you can, it is 1. You could use L'Hopital's rule, for instance, or you can divide the top and bottom by n squared, the highest power anywhere within a fraction. Limit turns out to be 1. So because it is non-zero, so you conclude that the series diverges. This test will never, ever, ever, ever tell you that a series converges. You cannot reach that conclusion at all you see in this test. Can only tell you divergence. If the terms do go to 0, all it tells you is it might converge. As an example, a harmonic series, sum of 1 over n. Go ahead and take the limits of the terms, 1 over n. You do get 0, but using a different test that we'll see later, the series still diverges. So be careful about not extrapolating from what this test tells you. In other words, this statement is true. Its converse is not true. So if a limit is 0, you cannot conclude that it converges. Given a logical statement like this, what form of it is true? Let's talk your discrete knowledge.
Diverge, then the limit of the sequence is not equal to 0.
Oh, you're so close.
So
You gotta flip both parts. Yes, if the convergence limit is 0. Okay, yes. Okay, so and yes,
So in the second example, it does diverge?
this series does, yeah, but you wouldn't find it out using this test. Yeah, it has, so if the terms do go to 0, the question of convergence or divergence is unresolved. But use a different test to be sure about that, like a one-to.
It's just like, I don't know if it's like the opposite of everything we've learned so far.
What?
Because 1 over n, it converges towards 0.
The sequence
Yeah.
does.
I know, it's just, that's gonna confuse me on the test if that's asked.
Yeah, the series does not. Okay. Okay. Now, whatever I mentioned earlier about the given a statement like this, in this case, the converse is not true. The equivalent statement is true. What do we call that? Contrapositive, yes. So contrapositive in this case is, if a series converges, the terms go to zero. Yes,
What's the but, does it, the second one does, right?
okay, I should be more clear about this. But okay, the sequence converges to zero, but the series, this series diverges. One more example. Over n squared, you take the limits. It goes to infinity, 1 over n squared. This is 1 over n goes to zero, certainly 1 over n squared is also going to zero. And this series happens to converge. So 1 over any power of n greater than 1, we will see converges, but this test is not telling us that. Okay. So another way of putting it is the terms going to zero is a necessary condition for conversion. It is not sufficient. Questions about the nth term test before we go to the next one?
Isn't it like the previous?
We'll use a p-test on series like these. That's coming.
Going to zeros and a greater than one.
Yeah, the power is greater than 1. Yeah.
It's only zero than a secondary condition for what?
For convergence, but not sufficient.
Oh.
Yeah, because so both of these series make that necessary condition. But as we can see from this series diverging, this one converging, that alone is not enough. Okay, next, we're going to talk about certain combinations of series. Let's suppose you're given two series of an sum of bn. Okay. So if the two series individually both converge, then if you take another series, but you're adding them up. That converges too. So the sum of two convergent series converges.
Question, would both of them have to have n equals 1 and have the same starting point?
If they don't, then like for example, suppose this one started at n equals 0, then you could leave that, set that term aside. And then you had, well, you could still describe the sum of the two series. It would converge in that case. So, because when you're combining series, you should write them in such a way that they start at the same point.
Okay, so that just should be given.
Yeah, that's why I wrote it this way. Now, also, we can conclude that the sum of the combined series is equal to limit the sum you get from the first one and the sum from the second one. So, for example, suppose A and B are two geometric series that converge. So you figure out the sum of each one using a formula from last time. So then the sum of a combined series would be the sum of these two that you get. And same can be said with subtraction. So the difference of two convergent series will also converge. And the limit of the difference will be the difference of the limits. Also, suppose you take one of these series that converges and scale it. So you scale each of the terms by some constant c. Then you can pull that out of the sum. So if you scale all the terms in your series by some factor c, that scales the sum by c. So all these, so it's basically the linearity of the series because you're summing things up. But you can count on these combinations working out. But only for addition and subtraction. I didn't say anything here about if you take two convergent series and you multiply them term by term. We don't have any conclusion about that.
Hold on, you had, why did you have an AN minus BN down there? What's that?
Well, it's a number combination for which we know what happens.
Oh, okay,
Yeah, so addition and subtraction work out the same way.
so it's, so, okay, so you're saying they were.
Yeah. Yeah, so the sum or difference of convergent series is convergent. And the limit of the sum or difference is what you get. Now, I'll also say, well, that one of the series diverges. And the other one converges.
Wait, that's what I just realized, why do you have a BN at the bottom of that?
Oh, sorry, it should be n. Would say that I'd be doing it, keep you on your toes, but I'd be lying. Okay, if one of the series diverges, the other one converges, then any of these combinations, sum or difference, will diverge. So any combination like that, it's not going to work out. If both diverge, it actually depends. You might think, oh, if I have two series that diverge, you add them together, then of course the result is going to diverge too. Usually that is true. But what if, when you add or subtract them, what if something cancels out? It's possible that the sum might converge, but the sum or difference might converge after all. So these are really definitive statements that we can make, that if they both converge, sum or difference converges. If one diverges, the other doesn't, then sum or difference will diverge. As an example, if I have equals 0 to infinity of n, and that is a convergent geometric series. Sum turns out to be 2. And then I have another convergent geometric series. That as a sum of 3 halves, using a formula a over 1 minus r to arrive at these, then you can conclude that this series obtained by summing the two is the sum of the two individual series. That'll be 7/2 in this case. What about these combinations of series?
Is that the same, like if we multiply or divide the series and the,
If you multiply and divide series,
yeah, like.
No.
and,
um,
yeah.
like, okay. I could take this series divided by this one, and I could divide the limits, but there's no easy way to express that quotient as a series. What are the terms of that? Can we figure it out? It'd be very difficult. Similar with a product of series, because you're basically doing an infinite FOIL, if you will. Yikes. Don't do that. And I won't make you do that. Kind of like with derivatives, for example. One of the first things to learn about derivatives is the derivative of a sum. F of x plus g of x is the sum of the derivatives. And same for subtracting. But if you multiply two functions or divide two functions, you have some rule to use. Next, we have what's called the integral test. It does talk a little bit of your Cal 2 knowledge for this. That's a little.
We're done with that.
So, start with an example. Suppose I have a series sum of 1 over n squared. Now, if I were to graph 1 over n squared, and this graph is not going to be entirely to scale, but the best I can. The graph looks something like this. Now, so this series starts off 1 plus 1 4 plus 1 9, and so on. So I could think of this sum as area of rectangles. So here I have a rectangle where the width is 1 and the height is 1, corresponding to this first term right here. Then I have a rectangle here. And so the width of all of these equal to 1. The height of this one is 1/4, corresponding to the second term. And then I have another one that's 1/9, corresponding to the third term. So this is a sum of the areas of rectangles. These rectangles. Now, you think of these rectangles as approximating the area under this curve, the graph of 1 over x squared. So that's what this curve is. Okay. Starting from x equals 1 going forward, up to infinity. Now, the area that we're getting from these rectangles will be greater than the area under the curve, just because you can see this rectangle is sitting above the curve, this one's sitting above the curve, and so on. But remember from Cal 2, your instructor may have had you approximate area under a curve using rectangles, and you're evaluating your function at either the left endpoint, right endpoint, midpoint, yeah. So here I've chosen left endpoint. What if I choose right endpoint? Well, then this would be the first rectangle of height 1/4. And then this would be my second rectangle of height 1/9. It basically takes all rectangles except the first and shifts them to the left. So left endpoint the area of my rectangles, that's my shorthand there, is greater than area under the curve of 1/x². If I use the right endpoint for my rectangles, then the area of my rectangles that excludes that tall one there is less than the area under the curve. So I can get an idea as to whether the sum of my series treated as sum of areas of rectangles is going to be a finite value or not by looking at the integral and getting that area. So what I can conclude is that if the area under the curve is a finite number, in other words, the integral from like 1 to infinity converges, then I can conclude that the series converges. Or if the integral diverges, the series diverges. And that leads to what's called the integral test. So I'm going to state conditions. You have to make sure these conditions apply before you use it. Okay. So the integral test is as follows. Suppose I define a sequence in terms of a function. I'm just taking my function f of x and I evaluate f of x at n equal 1, 2, 3 off to infinity, all the integers. Okay. Okay. And f of x has to satisfy these conditions. Okay, it has to be continuous. Well, let's face it, most functions to deal with in a calculus sequence are continuous most of the time. Continuous, it has to be positive. And very important, it has to be decreasing. And shut up. Okay. So be sure to check all of these boxes before you use the integral test. Then, if the integral from 1 to infinity of f of x dx converges, in other words, you try to evaluate it and you get a number, you get a finite value, not infinity. Then this corresponding series converges. But the rest of the test is this. If the integral diverges, in this case, the converse is true. If the integral diverges, the series diverges. So it is like an if and only if kind of deal. Okay. So you're given a series, you try to evaluate the corresponding integral, and whatever happens with the integral is what happens with the series.
And what is next to the x, f of x, what x?
So here,
Above that. Above that. There, what's next to the left of the x?
Oh,
Right, f
right.
of x.
that's a D. Now, the value you get from the integral is not the sum of the series, but it could be taken as an approximation of it. Any questions about the idea behind the integral test before I do some examples of using it? So really, the series itself is a Riemann sum corresponding to the underlying integral. It's just that you're just rectangles with 1. And as you let the width go to 0, then you're getting the exact value of the integral. That's because we can use the series to get an upper and lower bound for the integral. That this test works both ways. Right, so let's suppose I have sum of 1 over n to the p, where p is some positive real number. So the terms of a series will go to 0 as n goes to infinity. The larger p is, the faster the rate at which it goes to 0 will be. We're gonna use the integral test for this kind of series, so we can determine convergence or divergence for whatever value of p we have. Okay. So what we'll do is evaluate the integral of 1 over x to the p. This function is continuous for x between 1 and infinity. It's not continuous at 0 because it blows up as that vertical asymptote, but we're not integrating it over a domain involving 0, so it doesn't matter. Where we need it to be, it is continuous, and it's positive, and it's decreasing. So checks all the boxes for being able to use the integral test. Now, the way you would evaluate is called an improper integral because the upper limit is infinity. So really what you do is, just to be rigorous, is you consider an integral with a finite limit, which I'll call k, and you take the limit of that as k goes to infinity. So really the only kind of integral we're evaluating is one that has finite limits. To evaluate this, it's easier. We want to use the power rule for integration. Write it this way, x to the minus p. So then use the power rule. And what will that give you? So what's the antiderivative of that?
XP of it.
3 plus 1 divided, and the whole thing is divided by negative plus 1.
In most cases, yes. And yeah, I believe one case you're talking about is the exception. If so we're going to consider these cases separately. P is not equal to 1. Yeah, then the power rule applies. And I can write it this way: x to the 1 minus p over 1 minus p, which limits 1 and k. So you go ahead and plug in limits. And then you'll get over 1 minus p times k to 1 minus p minus 1. Okay. Now, we need to take the limit of this as k goes to infinity. And we want to see where we're going to finite number. So if k is going to infinity, What's gonna happen, under what circumstances would this whole expression go to zero?
One minus p is less than what is it? If it is negative, then it inverts and the k becomes 0.
Um,
1 minus p less than 0.
okay, so, sorry, I can't be sure if you're right because you were jumping around a little bit. So if P is,
If it's between 0 and 1,
okay, okay, so P in this case is, if P is greater than 1. Okay, then what happens? Yeah, yes, yes. Okay, yes, that is correct. Okay. And you were saying that if P is, okay.
both
So,
are.
so now we're already assuming from the get-go that the P is positive. We're also assuming that it's not equal to 1. So if P is greater than 1, then the integral. So this part's going to go to 0, k to the 1 minus P. Because you're going to have 1 over a larger number in the denominator. So k to 1 minus P can be written as 1 over k to the P minus 1. So we want that to stay finite. So in that case, if P is greater than 1, the denominator will get larger, the fraction will get smaller, it will go to 0. So we're left with 1 over P minus 1 in that case. So we can say that the integral converges. And then if P is between 0 and 1, this is going to go to infinity as k goes to infinity. So it diverges. The integral diverges, therefore the series diverges.
That's what I was talking about, the
Yeah.
between, yeah.
Yeah. One case is not covered. P is equal to 1. So then we're looking at as a limit of k goes to infinity of natural log of k. Since that rule applies, but natural log, that goes to infinity. This argument goes to infinity. It does so slowly, but it still does. So in that case too, it diverges. So the only time the integral converges is if P is greater than 1. So this special case of the integral test is called the P-series test. That comes from as a consequence of the integral test, that the sum of the series 1 over n to the p converges if and only if p is greater than 1.
Was that L in absolute value k?
Yes, it is.
Okay.
Because this case we don't really need the absolute value, but that's the rule. Okay, so the p-series test is what tells us that the harmonic series, sum of 1 over n, diverges. But 1 over n to even a slightly greater power, 1 plus anything, no matter how small, that will still converge. That's like the tipping point. And this is something that you use quite often. The knowledge of the fact that knowledge of this kind of series ever converging or diverging depending on what the exponent is. Well, this one. Yeah.
You say you use this for a harmonic series?
Yeah, so the harmonic series is the case where p equals 1. So this is one way of proving, if you will, that the series diverges. Here's another example. 1 over n squared plus 1. This satisfies all the assumptions. It is positive, it is decreasing, it is continuous. Now I want to evaluate this integral. So 1 over x squared plus 1. Does anyone remember the antiderivative of 1 over x squared plus 1?
Inverse tangent.
It is inverse tangent. Yeah, just 1 over x is log. Yeah. All right, so that is inverse tangent. Okay. So now if we plug in the limits, we're going to get inverse tangent of k minus inverse tangent of 1. What is inverse tangent of 1? Yeah, yeah, pi over 4. Also known as 45 degrees. Okay. But then it's a matter of what happens to arctangent as its argument goes to infinity. Does anyone know what that is offhand? You can try your calculator.
Can you
But
ask
like
the
a large
question
number.
again?
What?
Can you ask the question again?
What is this limit? What happens to arctangent as its argument goes to infinity? So another way, what angle will cause tangent to be plus infinity? What? Well, there's an angle at which at which tangent goes off to infinity. Because tangent is vertical asymptotes, yes. It is pi over 2, yeah. The final result is pi over 4 for the integral. So that tells us that this series converges because the corresponding integral converges. Okay, the notes I had from 0 to infinity, so I integrated from 0 to infinity. So the result is pi over 2, but the approach is the same, starting at different lower limits.
So what if our is like, not 1, if it's like 3?
Okay, so assumptions about the being positive, decreasing, continuous would still apply. So you could like integrate from, free to infinity if you really want to. As long as those assumptions are satisfied, no. So for example, going from 0 to infinity in this case would still be fine. But what if I started n at a negative value? The function 1 over x squared plus 1 behaves like this. So if I started out here, the function's not decreasing a whole. I shouldn't use that.
N equals 2, and then n is gonna be 1 over 3n.
Sorry, it's n equals 2 and 1.
So n equals 2, and then the an is gonna be 1 over 3n.
Oh, 1 over 3n.
Yeah.
Wait,
But
are you talking about? Okay, n starting at,
2,
okay, and that,
3 raised to n. Yeah.
okay. Okay, so in that case, there's different ways to see that the series converges. But you're talking about using the integral test on this. Okay, so in that case, you could use the rule for integrating an exponential function. Well, it could be applied here. It's probably not the easiest way to see that this particular series converges, but it could be done.
Okay.
Any questions about just one?
For like tests, are you gonna want us to remember? Cause I'll have to go back, but like what tan or inverse tangent is on the fly?
Okay, oh, like how a function itself behaves?
No, like 1/x² + 1.
Oh, but meaning integration rules.
Yeah, the integration. You want us to go back and remember those or relearn those?
This is Cal 3, not Cal 2. So, sometimes I will put relevant formulas.
Okay,
When we get closer to the midterm, I will make it known what information I'll provide. But you know, you won't have to study that. Okay. Like for even when it is Cal 2, I'm more interested in where we all can apply various integration techniques. Like given whatever integrand, do you know how to carry out integration by parts, substitutions, things like that, as opposed to like memorizing things. But in this day and age, we can just look things up. Okay. How am I doing on time? Not that great, but we'll get one more. And going from 2 to infinity over n times the natural log of n. So for that, you would look at the integral. And I had to start at n equals 2 because the natural log of 1 is 0. So if I start at n equals 1, my first term would be undefined. So you take it over 2 to infinity of 1 over x natural log of x. Now, in this case, because of time, I don't really want to go through the whole thing, but can anyone tell me what approach you would use to carry out this integration?
Substitution.
Yes, what is the substitution you should use? Yeah, you let u be equal to natural log of x. So then du is 1 over x dx. So this would be the integral from natural log of 2 to infinity of 1 over u du. Let's see, that would be natural log of x from x going from 2 to infinity. But what's that going to be when I plug in those limits? Yeah. The series diverges. I'm wondering, did I previously, I don't know if I previously said it converge. I hope I didn't. That's immortalized on YouTube if I did. But in that case, I was doing something in my head, which is really a bad idea in the middle of class. But when you're in front of a classroom teaching, your IQ is just. That's why I've prepared stuff when I'm thinking clearly. Okay, but here the integral test has spoken. So the terms 1 over n log n, they go to 0 faster than 1 over n, which diverges, but they still don't go to 0 fast enough. Whereas if I did 1 over n to the like 1.000 or something, only slightly greater than 1, that would still converge. Integral test. Questions about this one? Okay, I have 2 more tests to show you. Very closely related, called comparison tests.
Okay, question on the other one, why did you have ln2 at the bottom?
Oh, here it is integral with respect to x,
Okay,
but here with respect to u. So these limits will not apply.
okay,
What I have to do is take these limits and plug them in here for x to get the
Okay.
corresponding u values, and those will be the limits here.
okay.
But then down here, I undid the substitution and brought me back to X, which is why I'm back to the original limits of 2 to infinity.
Okay.
Usually when you're doing substitution, you don't bother changing the limits because, you know, you're gonna back to the original variable anyway, but I wanted to make sure I wrote the integral correctly. A comparison test. Right, so I just need to, of course, the time is running short, so I need to state these. And then I have some examples. Okay. So suppose you have two sequences, A and B n, that are both non-negative. And in terms of A n are less than or equal to in terms of B n. Now, here's the conclusions we can make. If series involving Bn converges. So the larger series converges. Smaller series also converges. Meanwhile, if the smaller series diverges, the larger series has to diverge too.
What if it's reversed?
Um,
So like if
Well-
A was larger,
It doesn't, that's
Oh, yeah,
like
we
a
need to
number
have that.
smaller than
Yeah, so-
the end.
yeah, so just because if this series already converges, because in terms of A and are smaller, there's no way that it's gonna go to infinity when it's always dominated by the other. So the other possibilities are inconclusive. So you have to be careful about that. Here's an example of that. I'll let AN be 1/2 plus 1. Bn is just 1/2. Turns out that AN is going to be strictly less than Bn. Yeah. Just because of AN, the denominator, by having a plus 1 in there, is going to be larger, therefore the whole fraction is going to be smaller. So then we look at the larger series. 1/2. Converge or diverge.
Is it going to infinity?
What?
The series there.
Oh, yes, it is. Yeah, finite series aren't interesting, but it does converge. Why? Or we do more than that though. Geometric series. Yeah, the denominator alone getting bigger is not enough to establish convergence. Like harmonic series doesn't. So this is converges. In this case, we would know the sum, but we don't really care about that here. So that tells you that this other series, 1/2 plus 1, that has smaller terms also converges. Because you have a difficult time figuring out the sum of this one because it doesn't fit the form of a geometric series. This, we know it converges because it's geometric. Questions about this one? Now, in this case, it's not too difficult to determine which series is the larger, just because both have the same numerator, and you're just looking at the denominator, which series has a larger denominator, and that's going to be the smaller fraction. But for some series, it can be difficult to tell which series is larger, which has larger terms. Also, it may not be, one series may not be larger than the other all the time. So here, a comparison test requires this relationship to hold for all n that are at least included in the series you're considering. Like, so in this case, n going from 0 to infinity. Right. Now, if my series are both starting at, say, n equal 5, as long as this relationship holds for n greater or equal to 5, then I'm good. But the fact is, it doesn't really matter what happens in the beginning for small values of n. What matters is what happens as n goes to infinity, what kind of relationship the series have. So the other convergence test, I actually like much better. I think it's useful in many more cases. And that is called the limit comparison test. That doesn't have such a stringent requirement. So in fact, you don't use comparison at all. Might as well use this one, I think. Okay. So we're given two series of an, of bn, and if this relationship holds, you take the limit of the ratio of individual terms as n goes to infinity, and suppose you get some constant c, where c is non-zero. So in other words, in the limit as n goes to infinity, these terms have a fixed ratio. Then you can conclude the following: that the corresponding series, one of two possibilities. Either they both converge, or they both diverge. Because if this is true, what it's saying is that in a limit, in the long run, as n goes to infinity, the terms of one series are basically a scalar multiple of the terms of the other series. So you would expect that they have the same behavior, and they do. But this is about growth rates of functions. If you have a series and you're trying to determine whether it converges or not, you can try applying the limit comparison test to a series that has, where the terms have the same growth rate or decay rate, but which you know whether it converges or not. So, as an example, squared plus 1 over n cubed plus 3n squared plus 2n. So it'd be pretty difficult to determine whether this series converges or diverges using something like the integral test, or maybe even the comparison test. But limit comparison test, we can come up with a series that's easy to work with by looking at in this case, we have a polynomial above and below. Look at the difference in degrees. We have n squared, second degree up top, third degree at the bottom. Take the difference of the two. So you carry out limit comparison test with 1 over n. So in other words, you ignore all but the leading terms above and below, and that tells you which series to perform limit comparison with. Limit comparison test, you take the limits as n goes to infinity of the terms of your first series divided by terms of second series. Doesn't matter which order you take them in. Because that's just the difference between getting either C or 1 over C. So then we're dividing by 1 over n. But that's the same as multiplying by n. So that'd be n squared, n cubed plus n, or n cubed plus 3n squared plus 2n. And what happens when we take the limit of that? We're going to get 1, because you look at the leading terms, there's a consequence of L'Hopital's rule, because the top and bottom have the same degree, which is why we chose this series to do the limit comparison test with, because that brings this outcome about. So because we have a limit that is a non-zero number, and we know that the second series, 1 over n, diverges by the limit comparison test, the other series must behave the same way. It must also diverge. So the way of like a homework problem work out, you'd be given just this series, and then you would figure out which is the best series to compare with for using the limit comparison test. But they basically taking a series that is the same rate of decay, but it's much simpler, but you know whether it converges or not. And then this limit will work out. Before I do another example, here's a guideline. If an is equal to value some function f at n, where f of x is a what's called a rational function. Can anyone tell me what is meant by a rational function?
They can be expressed as a ratio.
A ratio of what? Can't be just anything. Rational number is a ratio of numbers. Rational function, though, is a ratio of what kind of other kind of function? Polynomials. All right, so we have the polynomial of degree p up top, and that's polynomial of degree q down below. So when that happens, the series that you should compare with 1 over n to the q minus p. You look at the difference of degrees, denominator minus numerator. And then it's guaranteed that the limit comparison test will give you a limit that's a non-zero number. So based on whatever exponent you have down here, that is from p-series test, would converge if q, the difference q minus p is greater than 1. So in fact, you could just look at your rational function, look at the degrees and say, oh, it converges. You don't even have to carry out the mechanics of the comparison test because you know how it's going to turn out in that case. You can take that shortcut on a test as long as you still explain to me what you're doing. I don't want an answer that one you could have just as easily guessed. Here's an example that's not a rational function. Use a similar idea. We have n over square root of n to the 6 plus 1. So you still want to know the growth rate of a numerator and denominator. You just have to take the square root into account, figuring out what that growth, yes, it's
It's polynomial of what?
DEG, degree,
Okay, degree.
P and degree Q.
Okay, got it.
So based on the function we have here, n of 6 plus 1, but taking a square root of that, what would the degree effectively be? So what series should I do limit comparison with?
Wait, n squared.
1 over n squared. Yes. Why? Why is it n squared?
One n cube.
Obviously numerator, but denominator, yeah. So the denominator, we have n to the 6, but inside square root. So this one is, as n goes to infinity, it behaves like n cubed. Because this is n of 6 plus 1 raised to the 1/2 power. So you take that 1/2 power into account. So effectively, we have, as n goes to infinity, n over n cubed, or 1 over n squared. So this is the correct power to use. So then what you do is you take the limits. Then goes to infinity of the first series divided by the second. Now you're dividing by 1 over n squared, but that's the same as multiplying by n squared. But now I can write n cubed as square root of n to the 6th. Now I can express the whole thing as a square root. And we can see that, looking at what's under the square root sign, that fraction is going to 1. So then everything checks out. And because this series converges, therefore, this series also converges. Whereas if I had n to the 4th plus 1 under a square root, that would diverge by comparing with 1 over n.
A minus b values.
If you can figure out what is the effective degree of your function, then yes, it still applies. Questions about this one? So right now you have in your arsenal nth term tests for divergence, and then you have combinations of series, like the sum of two series that converges, integral test, comparison test, limit comparison test. And yes, I will be dropping more convergence tests on you, just a few more on Wednesday, and then we'll complete the set. But one of the things I'll give out when it gets closer to the midterm is like a one-page study guide which lists all the tests. So that will help you review all of them and when they can be used. This particular one is helpful much of the time because it doesn't require that your function be of a specific form. Like the integral test, what if you can't evaluate the integral? So there's only certain cases where that one is helpful. Like good luck using the integral test on this one, for instance, but you don't have to.
So wait, what was the n of square root of n power 6 plus 1? And 3, what's that? What's
This right here?
approximate? Is it approximate or?
In fact, as n gets larger and larger, this is approximately equal to this.
Okay.
Just because the 1 is so small compared to the end of the 6 that you can neglect it.
Okay.
And that's why you can say that it's approximately equal to. So for purpose of determining whether a series involving an expression like this converges or not, we can think of it as being like n cubed. Determine which series to compare with.
Okay.
More. Okay.